Okay, welcome to lecture. Sorry about that. I just had a little computer issue. All right, I think I got it worked out. We're continuing on talking about chapter 15, I think, here. Just give me 1 second. Okay, so in this chapter here, we started talking about Ksp, and Ksp is the equilibrium constant for really things that are sort of insoluble um, and sort of unique sort of to KSP type situations. Usually the reaction it always looks something like this. We have our solids going to our ions basically. So aqueous kind of on the right hand side of the arrow and solid on the left hand side of the arrow. So when we do write our Ksp expression, pretty much it's always just the products. So like something like silver chloride that we saw, when it does break apart, it breaks apart into silver and some chloride ions. And again here, it would be our products over our reactants. But as we can see, and what is usually the case here, our products are the only aqueous things there. Our solid is always kind of on the reactant side. So it really does end up being just our products in our Ksp expression. Now, everything, even though technically based on sort of solubility rules, it's insoluble, everything does have some degree of sort of solubility with it. And so even though we usually think of, say, something like silver chloride as being a solid insoluble, there is a small amount of it that will break apart and really set up this equilibrium that we see here. And we can apply an equilibrium expression to it. What we also saw was, as well, because of that, and that these equilibriums are really for things that are insoluble, really because of that, we see really small values of KSP. So typically speaking, the value of the KSP is usually a fairly small number. And really what that implies is, again, because it's an equilibrium, that pretty much mainly everything is staying sort of on the reactant side, which is our solid. And again, that's how we normally think of it, as being insoluble. But again, there is a small bit of it that will go to the other side. Now, we can have certain problems, as we talked about last time, that we have to do sort of an ice table. And if we were doing an ice table with something like this, like we saw the other day, we would approach it the same way. We would start with zeros. And the difference that we talked about is usually in sort of solubility type problems, we do use that S instead of an X, and really can use any letter you want. But that S does sort of refer to the molar solubility, basically the molarity. And again, we would carry our S's down and do like normal, put it into our equilibrium expression, solve for S. And that would give us our molar solubility of a particular compound. And it would be in moles per liter. If we wanted the solubility in something like grams per liter, we could use the molar mass and convert the molarity into grams per liter. And that'll give us maybe a more usable site of value for solubility. We also saw that pretty much because of the stoichiometry that's sort of involved and so forth, when you do solve for S, although S may be considered also the solubility of these individual ions, it will also be the solubility of the entire compound, as it's, again, in this particular example, a one-to-one relationship backwards, which means you do end up with really the same value of S for the solubility there of silver chloride. So that's how we could really relate back to our whole thing. It usually is just the value of S when you get that. We also then started to talk about sort of some things that do affect the solubility. And there are several things that affect the solubility. One thing we talked about at the very end last time, which was the common ion effect. And in the common ion effect, basically we have a ion that is in common with our solid, And because in these reactions, the ions are only found on the product side, that means based on Le Chatelier's principle, it should really shift the equilibrium back to the left-hand side. And it will keep pretty much that solid intact. And it will also decrease the solubility of a salt such as this, again, by forcing the equilibrium back to the left-hand side. And lastly, I think we also talked about the idea of you can, in certain cases, use the Ksp values to determine whether or not one substance may be more soluble or another substance may be less soluble. And remember that you can only really use the Ksp values when you are comparing basically two things that break apart into the same number of ions. So if I wanted to compare something like silver chloride and say silver bromide, like we might do a little bit later on, we can use the actual Ksp values to compare that. And the larger the Ksp value, the more soluble it would be. The smaller the Ksp value, the less soluble it would be. The place where we cannot directly use our Ksp values from the table to compare solubility, like we talked about last time, is a case where we're comparing substances that break apart into different numbers of ions. So if we have something that breaks apart into some different numbers of ions, we really can't use the Ksp values. So I think we looked at an example where based on Ksp, and those three examples that we looked at last time, we would expect, for example, the one with the sort of higher Ksp value to be more soluble. But in fact, what we saw when you actually did the calculation was it was opposite. It was actually the one that was the least soluble in all those. So when you're comparing things that have different numbers of ions in terms of how they break apart, you do need to actually do the calculation and do the comparison that way. Again, you can only use the Ksp value to compare if they are producing the exact same number of ions. Any questions on any of that stuff that we sort of talked about last time? Okay, so we talked about, like I said, common ions, sort of where we left off in terms of, get the right thing here. There you go. In terms of affecting solubility, another important sort of aspect of things that can affect solubility is actually pH. And the pH of a solution can have a pretty good effect on the solubility. And when we do have the common ion like we saw before, we do see that decrease in solubility. We also can see an increase in solubility if we're dealing with some type of insoluble base. So if we're dealing with an insoluble base, it is much soluble in acidic solutions. While alternative to that, if we have something that's an insoluble acid, we can basically dissolve it in a basic solution. And we're going to talk why that is right now. So for example here, if we look at this guy, that is magnesium hydroxide, and it breaks apart into magnesium plus a couple of hydroxide ions. This particular guy has a Ksp, as we can see here on the screen, of 1.2 times 10 to the minus 11. And if we go through and sort of do our Ksp sort of calculation here, we have our magnesium hydroxide going to magnesium plus a couple of hydroxides. And if we did our ice table here, this would be 0, 0. Our change would be plus S plus 2S, and at equilibrium, we would have S and 2S. If we put this into our Ksp expression, this would give us S 2S squared equals 1.2 times 10 to the minus 11. That's going to give us something like 4S cubed is equal to 1.2 times 10 to the minus 11. And when we do that, that does give us, if we take 1.2 to the minus 11 and divide it by 4, and then take the cubed root of it, That gives us something like 1.4 to the minus 4 molar as our molar solubility here for S. Now, when we're talking about pH, obviously the pH is equal to minus the log of the H plus. We also know that pOH is equal to minus the log of the OH minus. So here, because we do have hydroxide, we can substitute our S into here and get the equilibrium concentration of hydroxide, which would be 2 times S. And if you take 2 times S, you will end up with 2.9 times 10 to the minus 4 molar. And if we then put that obviously into our pOH minus the log of 2.9 times 10 to the minus 4, we get a 3.54 and a pH of about 1046 here. So what I just calculated, give or take here, depending on rounding, is the pH of this solution to start with. So if you made this sort of magnesium hydroxide solution-ish, this solution here would have a pH of about 10.46. Any questions first off on that calculation? That is sort of your baseline pH for this particular substance here, this magnesium hydroxide. So we want to think about what would happen if, for example, we take a pH and we lower it. If we lower it below 10.46, the pH. So at a pH of less than 10.46, the only way to do that, right, is you would probably have to add some acid. So you are adding some acid, which is H plus is being added. And when we look at our equilibrium here, if we add some H plus, the H plus would most likely react with our hydroxide. Those two guys will make our good friend water. But more importantly, what it's going to do if you lower the pH less than 10.46 is it is essentially going to be removing OH minus. And when we would remove OH minus, that's going to cause the equilibrium to shift towards the OH minus and cause that equilibrium basically to shift to the right. And again, when we look at this equilibrium, to the right is our aqueous ions, and that should increase the solubility. And that's what it means when it says that an insoluble base such as this is soluble in acidic solutions, because when you add the acid, you are essentially removing the hydroxide. When you remove the hydroxide, it causes the equilibrium to shift to the right and obviously make more of it dissolve. Any questions on that? So if we look at this and decide, hey, what would happen if we did the opposite? So let's say we went above. Let's say we went above 10.6 or 46. So we took the pH above 10.46. When we take the pH above 10.46, in order to do that, we essentially need to add probably some base. So the OH minus is added, basically. And when we add OH minus, that is also not going to be removing our hydroxide, but in this particular case, it's going to be like adding more hydroxide. So it's like adding more hydroxide because you are. And when you do that, it's going to shift away from the side you added it to. So we would expect the equilibrium to shift to the left here. And when it shifts to the left, it is obviously going to make more solid. And when it makes more solid, that obviously would decrease the solubility. So as you can see from this example, the pH is really important as well, especially when you're dealing with acids and bases that are insoluble, that having the right pH can affect whether or not you would anticipate something to dissolve or something to be a solid. So for example, if we had some magnesium hydroxide here, we would maybe expect it to be a solid based on some solubility rules and all that good stuff. But if we put that magnesium hydroxide really in a solution that's, less than 10.46, we won't see the solid. We do need to get that solution to like a pH of 10.46 in order to actually see that solid appear. So again, pH can definitely play a factor in whether or not you, again, do see, something dissolve or something maybe not dissolve. Any questions on that there? So we've seen now a couple of things that can affect solubility. We've seen the common ion affect solubility. We also see that pH can play an important role in, whether or not really, you see what you expect to occur. The other really important thing in terms of solubility is also concentration. Now, again, just because of rules on solubility rules that they say when you put these things together, you're going to get a solid. Again, it is important the sort of situation that's occurring as to whether or not you'll actually see that solid being formed. So another important factor really is the concentrations of the ions that are in solution. In some cases, if you don't have the proper concentration of those ions, even though you're supposed to technically see a solid form, the solid may not form. And that's where we come back to our Q versus Ksp sort of relationship. So earlier we talked about Q, and Q again is basically the reaction quotient. Is that same situation that we had earlier where we're not necessarily sure we're at equilibrium. So we oftentimes use our initial sort of concentrations. But here again, when you calculate Q, it is calculated the exact same way as you would calculate the Ksp. And then we would again compare. And a reminder, as we've been talking about solids again on the reactant side, products are our aqueous ion. And if Q is greater than Ksp, it'll go opposite the way it's pointing, and you would expect a solid to form. If Q is less than the Ksp, then it goes opposite the way it is pointing, and you would expect no precipitate basically to occur in that case. So let us take a look at one here. If 2 milliliters of 0.2 molar sodium hydroxide is added to 1 liter of 0.1 molar calcium chloride, will a precipitate form? So when we kind of go through this stuff, we do want to kind of think about the ions that are present, and we do want to think about, what possible combinations that could come together to form some type of solid. So for example here, obviously sodium hydroxide is not a combination that forms a solid since it's a solution. So our other option would be the sodium and the chloride coming together, or the calcium and the hydroxide coming together. So again, if you look at those sort of combinations and you remember some of your solubility rules, really the only one that is possibly going to make a solid is calcium hydroxide. So in this combination, if we poured both of these solutions together, our only possible sort of solid would be calcium hydroxide. So really what we want to figure out is Q for calcium hydroxide. Now the Ksp for calcium hydroxide, if we look it up on a table, is 8 times 10 to the minus 6. So to calculate Q, first off, since calcium hydroxide is our only possible solid here, we would write our reaction. And in this particular case, our Ksp expression, as we can see here, is our calcium and our hydroxide squared. Now we need the concentration really of calcium and hydroxide so that we can put it into our Q expression. And our Q in this case would also be the exact same thing. So Q is our calcium times our hydroxide concentration squared. So again, Q calculated the exact same way as Ksp. So we need to think about where we're going to get these things from. So calcium, the only source of calcium is our calcium chloride. So we need the actual concentration of calcium in this mixture when we put them together. So that's going to require an M1V1 equals M2V2 situation. I'm going to convert this into 1,000 milliliters just to get my volumes all the same units. You could leave it as liters if you want, but I will just do that just to make it a little bit easier, the math, I think. So for our calcium, which is going to come from our calcium chloride, we would need to figure out its concentration. So we would have 1,000 milliliters times its molarity of 0.1 molar divided by our total volume here, which would be 1,002 milliliters. Again, 1,000 milliliters of calcium chloride, and we're dumping 2 milliliters of sodium hydroxide in there. And that gets you something like, we'll call it 0.0998 molar for our hydroxide. The only source of hydroxide here would be our sodium hydroxide. So we're going to do the same calculation for our sodium hydroxide. We're using 2 milliliters. It is 0.2 molar divided by our total volume of 1,002 milliliters. Obviously, you could do everything in liters if you wanted to. Should come out the exact same. Really your call. That's going to be 4 to the minus 4, something like that. Any questions on how I got those numbers? And I don't have to worry about anything else here. For example, with calcium chloride, when that breaks apart, that's a calcium plus 2 chlorides. So it is a 1-to-1 relationship between the calcium ion and the calcium chloride. So that's why the molarity is the same. And same thing with our sodium hydroxide. If you broke that apart, it's a 1-to-1 relationship between sodium hydroxide and the hydroxide ion, which means it would be the same. Now that I actually do have the calcium concentration in the mixture and the hydroxide in the mixture, I am now free to actually put this into my Q expression, and that would give me 0.0998 times 4 times 10 to the minus 4 squared. And if I do all that here, so we're square it and times it by 0.0998, that is going to give me a Q value of 1.6 times 10 to the minus 8. Any questions on that? So now that I have my Q value and now that I have my Ksp value, I want to compare them. And here I see that Q is less than the Ksp. And because Q is less than the Ksp, that means that, again, it should shift towards the product side, and that's aqueous ions, and we would expect no precipitate here. Question on that. So as you can see here, although based on solubility rules, we would expect a solid to form with calcium hydroxide, our concentrations of those ions are not enough to actually see the precipitate form. And that's a very common thing that occurs. Again, just because solubility rules tell you it's going to happen, you do need really the right conditions to allow it to happen. And if you have not the correct amount of concentration, you may not see it. And this is a common problem. We don't really do that experiment too much at this school anymore, but you used to do a lot of experiments which are known as qualitative analysis. And in qualitative analysis, you essentially have a lot of ions that float around in the solution, and your goal is to sort of add a bunch of reagents to get things to precipitate out. And a very common thing that occurs a lot of times is people add too much reagents, too much water, something like that. And at some point, what you're doing, even you may not visualize it, every time you add a reagent, most reagents are solutions. Most solutions have water in it. So every time you sort of add a few drops of this or a few drops of that, although you are adding the reagent you intend to do, you're also diluting your solution a lot because you're adding more volume. And in certain cases, especially in something like qualitative analysis where you're kind of selectively precipitating out things, if you're not really careful in those situations, you may actually dilute your solution so much that even though you're supposed to see a solid form, you actually don't see it form. And that's a very common sort of thing that occurs in those type of reactions, or just reactions in general, not meaning to do so by adding other reagents. You sometimes are kind of over diluting things. And again, it could affect the ability to actually see something precipitate out. Any questions on that? Okay. So we've now seen really three sort of things that can sort of affect solubility. One is a common ion. Two is the pH of the solution. And three is the concentration of the ions, or really dilution. So again, there's a lot of factors that really can play a role into whether or not you do see a precipitate form or not see a precipitate form. So again, sometimes we get into the habit of thinking our solubility rules are for every single situation, no matter what the situation is, I should see it. And that's why, again, sometimes you don't see it. And maybe you've done experiments in the past in chemistry classes where you would anticipate a solid being formed and you actually don't necessarily see it happen. And these are some explanations as why it may not happen. Now, if everything's kind of going good and everything's sort of ideal, we could also use Ksp to do what is sometimes referred to as selective precipitation. And that's really the basis of what I was just talking about, a certain type of experiment that years ago in this class you would do nonstop. Every lab would be qualitative analysis. A lot of schools don't do it a lot anymore. But the whole point of this is sort of selective precipitation. And the idea here is in something like, for example, if you did qualitative analysis, you would have literally a test tube, for example, of a bunch of different ions that are floating around in the solution. And your goal is to try to identify what ions are in the solution. And to do that, you do have to be careful with how you proceed. So, for example, if we look at something like what we see here on the screen, that if we have a solution that contains some bromide ions, some chloride ions, and we want to precipitate these guys out, and we basically are going to use silver as a precipitating reagent. So you grab the bottle like silver nitrate or something like that, and you add it into there. Now, based on solubility rules, both silver chloride and silver bromide should both precipitate out, and they will. And in fact, if you look at these two test tubes on the right, one is silver chloride and one is silver bromide. And if you were trying to separate these two guys out and you added silver, there would be really no visual way to separate out what is the bromide and what is the silver chloride. You can't go like, I think this white crystal is like the silver chloride. I think this one is the bromide. Again, they're basically both the same color, which obviously, if you were doing something where it was really important to know you got, say, the silver bromide out, you would have really no way to knowing that you did that. So one aspect of sort of KSP is that we can use it to our advantage to do something known as selective precipitation. And what that means is what we want to do is basically take out only like one ion at a time. So we want to take out, in this particular example, just the bromide. So we want to precipitate it out as silver bromide. And we want to leave the chloride still floating around in the solution. So we could use the KSP of each of those guys to help us do that. So basically what we need to know is how much silver can we add to start the precipitation of just silver bromide, but really not precipitate out the chloride that's in that solution. So if we look at, say, our silver bromide here, and we write our Ksp expression for it, it would be the concentration of silver times the concentration of bromide, and that would equal 7.7 times 10 to the minus 13. Now, in this particular case, we actually know the concentrations of each of these guys. Both of these guys have a concentration of 0.02 molar. So that was given to us. So if we rearrange our Ksp expression and solve for silver, and if we put our numbers in, because we do have the concentration of the bromide at 0.02, we end up getting something like 3.9 times 10 to the minus 11 molar. So what does that number mean? That number means that is the minimum amount of silver that is needed to be added in terms of its concentration to that solution to start to see silver bromide start to precipitate out. So before you get to 3.9 times 10 to the minus 11, you could dump some silver in there and you're not going to see any precipitate. As soon as you hit 3.9 times 10 to the minus 11 in terms of the concentration of the silver, you should start to see some white solid form. And you will probably know that that white solid at that point should be the silver bromide. And that solid that would be coming out would be taking the bromide out. Now we could do the exact same calculation for our silver chloride. And if we do that, again, our silver times our chloride equals 1.6 times 10 to the minus 10. Solving for the silver chloride, doing the same calculation here. Divided by our chloride. Again, we know our chloride is 0.02 as it was given to us in the problem. And if we do that, that is going to give us something like 8 to the minus 9. And what that number represents is the minimum amount of silver that's needed to start to see silver chloride come out. So those two numbers are really important in this sort of question, because in this question, we want to take out just the silver bromide. So what that means is we do need to get the concentration of silver above 3.9 times 10 to the minus 11. But we need to keep the silver concentration below 8 times 10 to the minus 9 molar. So let's talk through what would happen as we sort of do this. So if we have this test tube here or whatever it may be that has, again, the chloride ions floating around and the bromide ions floating around. If we pick up our bottle of silver nitrate, whatever it may be, off of the shelf, and that concentration of silver is 3.9 times 10 to the minus 11, like I said, we can start adding it. And at that point, we should start to see a white solid that's being formed. And again, that white solid should be silver bromide. And you can actually continue to increase the concentration of silver as long as you keep it below 8 times 10 to the minus 9. So you may increase the concentration of silver and increase it. And at some point, you will probably start to see no more solid precipitating. And at that point, if you start to see no more solid precipitating, you could feel pretty confident that the solid that you do have should be all of the silver bromide. And you basically have precipitated out all of the silver bromide or the bromide ions in solution. Again, you can bring that concentration of silver all the way up to just below 8 times 10 to the minus 9. And again, you shouldn't see any solid at that point. You may continue to see solid, but at some point, if you just keep adding, in theory, you will stop seeing solid because you probably removed all of the bromide from the solution. At that point, once you've done that, you could centrifuge it, pour off the liquid, which should just contain the chloride at that point. You then can bring the concentration of silver to 8 times 10 to the minus 9. And at that point, you should start to see some more solid being formed. And that solid, once you get to 8 times 10 to the minus 9 or above, should start to be the silver chloride that's coming out, also a white solid. So this is a way that you could use Ksp to, again, selectively precipitate out one ion while leaving the other one in solution. And in both cases, the precipitating reagent is silver. So even using the exact same precipitating agent, like silver in both cases, by controlling the concentration, which, as we just talked about, is really important in terms of seeing solubility or not, we can basically control which ion will come out of solution first, and then we can take the next one out second. First off, any questions on sort of what's going on here in this problem? Now, could we have predicted that silver bromide should precipitate out first? And in this case, we could have predicted that if it didn't tell us to do it that way. And to explain why it basically told you to do it that way, let's take a look at something that we can look at, which is our Ksp values. So in this particular case, if you remember, our silver bromide here breaks apart into 2 ions. Our silver chloride also breaks apart into 2 ions, which means we can directly look at our Ksp values here. And what we see here is the Ksp value for silver chloride is much larger than the Ksp value for silver bromide. And because the Ksp value for silver chloride is much larger, it should be more soluble. And that's why in this problem, they talk about precipitating this guy out first, because it's actually less soluble in this comparison. So this is also a good example that in this particular case, because they both break apart into 2 ions, you can use the Ksp values and compare them directly. Any questions on any of that there that we just talked about? And this idea of selective precipitation is an important sort of thing. And again, we don't do that experiment at all anymore. In person, we do it, but sometimes we do this experiment, but we don't do it anymore to the extent we used to. But again, a whole sort of part of second semester general chemistry used to involve in labs experiments, which are basically known as qualitative analysis. And they're really these type of situations where we sort of selectively precipitate out different ions that are based together on groups. So when you do qualitative analysis, there's group 1, group 2, group 3, group 4, and group 5. And group 1, 2, 3, 4, and 5 is not related to the periodic table groups, but they are grouped together by basic solubility similarities. So, for example, group 1 is our silver, mercury 1, and lead 2, which based on solubility rules is soluble in everything except when you got chloride that has one of these guys. So we use something that has chloride in it, and that gives us these guys that precipitate out as chlorides. When we get to group 2, these are all guys that precipitate out with basically sulfide. Also, group 3 does as well, precipitates out with sulfide. But the difference here, as we were talking about, is the pH of those solutions. By keeping the solution acidic, we're able to precipitate out these guys, but it won't be enough to precipitate out these guys. So then we have to make the solution basic. So again, here using something like pH that we talked about allows us to kind of selectively precipitate out these different ions. Again, even using the same actual precipitating reagent. In that case, that's hydrogen sulfide gas, a pretty toxic, deadly green gas, and our toxic yellow gas. It smells like sulfur, not so great. But again, it's the same precipitating reagent for both of those groups. But again, by manipulating the pH of your solution when you're doing this, it allows certain ions to stay in solution long enough to allow other ones basically to come out of solution. And then like group 4 or 5, these are typically ions that are pretty much soluble in most things. So down here, we usually get to things like flame tests and stuff like that to identify them. And if you've done a flame test before, sometimes it's not the easiest thing to sort of identify. As you can see here, ideal flame test situation, but usually they're not very ideal. Any questions on Ksp, common ion, pH, concentration, any of those things? Okay. All right, so the next thing we're going to talk about is another aspect of equilibrium, and it involves complex ions. So complex ions are basically a metal, a lot of times like a transition metal, that's attached to one or more molecules or ions. These molecules or ions are what are referred to as being ligands. Ligands are what are known as Lewis bases. So we talked about Lewis bases in the last chapter. Lewis bases are things that will donate a pair of electrons. So something that can donate a pair of electrons, something that's really good at sort of doing that is something usually with like a negative charge, something that has gained electrons, something that is polar, that has some non-bonding electrons that it could share. Those are really good ligands. So this here is cobalt, which is our metal. And this is our ligand here, Cl minus, and making our complex ion here, which is a cobalt in the center attached to 4 Cls. And it can set up an equilibrium. And surprisingly enough, we will add this to our ever-growing list of K values. This is what is known as Kf, or the formation constant. And that is the equilibrium constant for a complex ion. And it is just like every other equilibrium constant that we have that we could add to our ever-growing list of K values. But Kf is our products over our reactants. So we have our products over our reactants here. And as the Kf value increases, so does the stability of the complex ion. So basically what that means is as our K value gets larger, the equilibrium will lie to the right, and to the right is our complex ion, and it will want to form that complex ion. By the way, these ligands do come on basically one at a time. So in the case of this guy, the cobalt would take on 1 chloride first and make COCl plus. And by the way, this would have a K value associated with it. Then what would happen is this guy here would pick up another Cl minus and make COCl2. Also have a K. Then our COCl2 would pick up the third one and make this. Also could have an equilibrium. And lastly, our guy here will pick up our last ligand and make our COCl4 2 minus. Also have a K value associated with it. So although we sometimes see the overall reaction that's occurring, ligands do come on in a stepwise fashion. And to get to that overall reaction, you essentially add together all those things. So we would add together all those guys and cancel out what's opposite. So this guy would cancel. This guy would cancel. This guy would cancel. And that leaves you, if you added up, 1 cobalt on the left-hand side plus 1, 2, 3, 4 Cl minuses gives you your complex ion on the back end here. By the way, if I wanted my Kf, since I added all these reactions together, the Kf in this case would be K1 times K2 times K3 times K4. So remember that when you add up equilibrium steps, you multiply the K values together. Any questions on that there? There's a couple of examples of some of these cobalt guys, and you can see different ligands beneath my writing there. You know, on the left-hand side is basically a cobalt with 6 waters attached. On the right-hand side, that's our cobalt with our 4 chlorides attached, and you can see some different sort of properties there. One's pink and one's blue. Some common ligands, and we'll talk more about these guys in a later chapter as well, but water's a good ligand, NH3 is a good ligand. Again, if you look at water, it looks something like this. It's polar, it's got those non-bonding electrons it can share. NH3, same deal. Chloride, again, has a negative charge and some electrons and stuff like that. Now, the number of ligands that are attached directly to the metal is what is known as the coordination number. So for example, here, this is a cobalt that has basically 6 waters attached to it. Since water is neutral, cobalt has a +2 charge. This overall thing has a +2 charge. Now, when we look at something like water, or actually any of these guys here, these are what are sometimes referred to as being monodentate ligands. Monodentate means that for every one of the water molecules, only one atom is attaching. It's the oxygen in this case, by the way, is attaching to that. So in each of these, the oxygen's attaching. So that's 1, 2, 3, 4, 5, and 6 for its coordination number. Same thing when we do our cobalt that has the 4 chlorides attached. It has a coordination number of 4. Sometimes people think, well, the coordination number is always going to be this number that is here. And that's not really the case either. So for example, if I had something like cobalt C2O4 2, and we'll say this is we'll go -2. If we had something like this, you may be tempted to go, well, obviously the coordination number here should be 2. And that would be incorrect here. The coordination number here would actually be 4. And that is because C2O4 2 minus is oxalate, and oxalate looks something like this. And when you have something like oxalate and it attaches to our cobalt, I'll just put a circle. This oxygen here can attach, and this oxygen here can actually attach to the cobalt. So for every one oxalate, you actually get two attachments, and oxalate is what is known as being bidentate, which means it could attach in two places per molecule. So if you had two of these oxalates present, just draw it to the side here, this oxygen and this guy would be able to attach, and this oxygen here would be able to attach, and that is 1, 2, 3, and 4 for the coordination number. So we'll see more of that, like I said, in a later chapter, but it's not always the little subscript there as for the coordination number. It does depend on the ligand, and some ligands can attach in one place, some ligands can attach in two places. Some ligands can attach like in 6 places per molecule. So, there's a lot of different types of ligands that are out there and how they attach. Any questions on that there? Okay, so let's talk more about the calculation part here. So let's say that we want to figure out if we mix together 0.2 moles of copper 2 sulfate with a liter of 1.2 molar ammonia, what is the concentration of copper 2 at equilibrium? You'll be able to, you have to tell the coordination number by it's how many atoms that are attached directly to the metal. So in the case of water, when water attaches, it's just attaching through the oxygen. So for every water that's attached here, there's 6 total attached to the metal, and each one will only attach through the oxygen, which again gives you 1, 2, 3, 4, 5, and 6 atoms that are directly attached to that cobalt, and it would have a coordination number of 6. And that's because, again, water here is monodentate, only attaches one place per water molecule. When you take something like oxalate, like I did down here, oxalate is what is known as a bidentate ligand. It could attach in 2 places per molecule. And that means that if you had 2 oxalates like we had here, one oxalate would be able to attach in one place, that would be 1 coordination number, and also 2 places, that would be 2 coordination numbers. The second oxalate would also attach in one place, that gives us now 3 for a coordination number, and this oxygen here will also attach, which would give us 4 for a coordination number. So it does come from knowing the different ligands, knowing how many places per molecule that ligand could attach. And if we had to say monodentate, it's simple, it's pretty much how many molecules there are. If it's something like bidentate, you have to take that into account. So again, sometimes people would look at this and go, oh, there's a 2 here, that should be the coordination number. But it's not, because each of those oxalates in that particular case has the ability to bind in 2 places per molecule. And again, we'll see more of this in a later chapter when we talk more specifically about complex ions and ligands and stuff like that. Probably not super important for this part of the chapter here. It'll be more important later on in the chapter. Other questions on that? Okay. So let's take a look at calculations that do involve sort of Kf calculations here. So we want to mix the copper 2 sulfate with a liter of ammonia. What is the concentration of the copper 2 at equilibrium? So we're going to assume in this case that the total volume here is going to remains 1 liter, just to make the calculations easy. So everything's going to be 1 liter. Again, won't always be the case, but just to kind of show you how this calculation happens, we're going to keep it that way. So let's take a look at it here. Okay. So we have our, equilibrium reaction written here. We are going to do a ICE table. So initially, if everything is 1 liter, we would have 0.2 basically divided by 1. So we will have 0.2 molar here. For our NH3, it will be 1.2, and this would be 0. Now, when we look at this Kf value, which is times 10 to the 13, that is a very large value of K. Remember that above 1 is large, so 10 to the 13 is a very large value for K. And that is usually the case when we see Kfs. So Kfs are typically very large numbers. And what that means is what we would expect to happen is because this is so large, we can make an assumption that pretty much the reaction is heading all the way to the product side. And we will assume because of that, that all of the copper in this particular example will get used up. And we make that assumption because on the product side, that's our complex ion, which means in order to make the complex ion, we need the metal in the middle. The metal is kind of like the limiting reagent in this case. That means that all of the metal should get used up. So different than how we would normally do the ice table, where we would do minus x minus 4x plus x and carry it down 0.2 minus x, 1.2 minus 4x, and x, we actually know what x is. X is actually going to be the metal. So when we do this ice table, I'll just write it underneath. What we assume is that the change is going to be the metal. So we could actually put the number in. It would be 0.2. This would be minus 4 times 0.2. And this would be 0.2 plus, which means at equilibrium, we will have 0 of this guy. We will end up with 1.2 minus 4 times 0.2, which gives us 0.4 and 0.2. Any questions on that so far? So we are interested in what is the equilibrium concentration of copper 2. And you may say to yourself, then it must be 0. And it wouldn't be much of a problem if the answer is 0. So we assume that all the metal is going to be used up in this type of situation because the K value is so large. But we do have to remember that this is a reversible reaction. So even though that almost 100% of it is heading in this direction, it is reversible, which means even a small little bit is going to head back the other way, which means some of that product will break apart into those ions. So the second part of the assumption is, although most of the copper should get used up in the complex ion, there should be a little bit of free copper left over. And that means that the concentration should be really, really small. So although we zero out the copper here, we then are going to come back and call it X so that we could solve for it. And what that means is if we go into our KF is our product divided by our reactants and that equals our 5 times 10 to the 13. Put it in our equilibrium now with our X for copper. That's going to give us 0.2 divided by X times 0.4. Don't forget, we still need to take it to the fourth. That's going to equal 5 times 10 to the 13. We're basically going to swap places and solve for X. X in this case will equal 0.2, 5 times 10 to the 13, and 0.4 to the fourth. And if we do that, we will end up with a value of x of 1.6 to the minus 13. And that would equal the copper 2 plus equilibrium concentration. And as we mentioned earlier, 1.6, that 1.6 times 10 to the minus 13 would pretty much classify as a very small amount. So that is definitely a very small amount. And that does justify our assumption. Again, we're assuming that pretty much everything's going to the product side and all the copper is getting used up. But we do have a very, very super small amount of free copper still in there. That is like 1.6 times 10 to the minus 13. That's almost like having none, basically, right? You have to go all the way out to like 12 decimal places to find the amount of copper in this particular example. And that validates that pretty much most of all of it, almost 99.9% of it, is in the complex ion, but you still have a super small amount that is still free. Question on that calculation there. And again, we make this assumption because KF values are typically very large values. And we can make that assumption here. Any questions on that there? Okay, so let's take a look at another one here. We want to calculate the silver concentration and pretty much everybody's concentration when we mix together 150 milliliters of 1 times 10 to the minus 3 molar silver nitrate with 200 milliliters of 5 molar sodium thiosulfate. So in this particular case, we have a stepwise complex ion formation given to us. So we got 2 K values, one for each of those steps. So first off, though, we want to think about the two sort of things that these guys are sources of. And obviously here, silver nitrate is a source of silver ions. Our sodium S2O3 is a source of our S2O3 2 minus. So that's the source of our ligand. This is the source of obviously our metal. So we really do want to get the concentration of these guys in the mixture. So again, that's going to be an M1 V1 equals M2 V2 situation. So looking at our silver, it looks like we have 150 milliliters times 1 to the minus 3 molar divided by the total volume. So here we are mixing 150 milliliters with 200 milliliters, and that should give us something like 350 milliliters in this particular case. That's going to give us 150 times 1 to the minus 3 divided by 350. And that should give us an opening concentration here of 4.29 times 10 to the minus 4 molar for our silver. We want to do the same thing for our S2, our ligand, basically, 2 minus. And for that guy, we're taking 200 milliliters, and we're timesing it by its concentration of 5 molar divided by our total volume also of 350 milliliters. And that's going to give us something like 2.86 molar. So here we're getting the concentrations of our ligand and our metal in the mixture. We could also add together these two reactions, these stepwise reactions, and get our overall reaction that's happening here. And in our overall reaction, basically when we add this together, this guy and this guy will cancel. It gives us silver plus 2 of our ligands going to make our complex ion in this case. 3 minus. So if we want to, we could work with the overall reaction that's happening by adding these stepwise guys together. And now we could kind of work this ice table like we did the last one. So I'm going to start with that overall guy and our concentrations of these guys. So taking our overall reaction there of silver plus our 2S2O3 2 minus gives us our silver S2O3 2 3 minus. So initially we have 4.29 times 10 to the minus 4 and 2.86 on this guy and 0. Remember that we're going to assume here that all of the metal is going to be tied up in our complex ion. So that's usually the case. So our change is going to be the metal here. So we're going to go minus 4.29 times 10 to the minus 4. This is going to be minus 2 times 4.29 times 10 to the minus 4. That's equivalent to like minus 2x. That's the equivalent to minus x, the first guy. And this would be like plus x, which would be plus 4.29 times 10 to the minus 4. That's going to get us to equilibrium, where our assumption is we're going to use up all of our metal here. We will end up with 2.86 minus 2 times 4.29 to the minus 4. We also end up with 2.86 pretty much, and 4.29 times 10 to the minus 4. First off, any questions on that so far? From our very first ice table that we just did here, we actually have the answer to 2 questions. First question is, what is the concentration of S2O3 2 minus? So the concentration of S2O3 2 minus is 2.86 molar. We also have the concentration at equilibrium of our complex ion from this first table, which I think was also something else they were on to know, 4.29 times 10 to the minus 4 molar. So again, just from doing that first table, we were able to get this guy's concentration. We were also able to get the ligand's concentration, but we still need to find out 2 more concentrations. We need to find out this guy, and we need to find out this guy. So there is a couple of ways that you could do that. I'm going to show you the first way here. Now that I have these guys' concentrations at equilibrium, I could potentially go back to each of these individual K reactions that I have here, these stepwise reactions, and use them to help me solve for what I'm missing. So if I look at K2's reaction here, K2, I have this number I just solved for, and I also have this number that I solved for. That would allow me to figure out one of the missing things I'm looking for. So I'm going to do that. I'm going to go back to using just the K2 reaction. And the K2 reaction, again, is that bottom one. And if we look at the K2 would equal our guy here. Divided by this guy here, which is what we're actually looking for. And our S2O3 2 minus. And this equals 3.9 times 10 to the 4. So what I am doing now is using just this second equation. And I could do that because it's an equilibrium equation. I have equilibrium concentrations. And that's going to allow me to solve for this guy. So if I solve for that guy, the Ag S2O3 minus is equal to, and I'm going to put the numbers in. So this is going to be 4.29 times 10 to the minus 4 divided by 3.9 times 10 to the 4 and our 2.86. Again, rearranging, basically these two guys switch places. And what that will give me is that gives me something like 3.8 to the minus 9 if you do scientific notation, or a bunch of zeros and a 4 at the end if you didn't. And that now gives me the concentration of the third thing I'm looking for, which is this guy. Any questions on that there? Okay, now that I have this guy's concentration, if I look at K1's reaction, I now have this guy's concentration and I have this guy's concentration. I now could use the K1 reaction and figure out silver's concentration. So we'll do that. So taking the K1 reaction, that is silver. Looking at this one here, silver plus our S2O32 minus, giving us silver S2O3 minus, and our K1, which is 7,4 to the 8. And solving for K1, which would be our product divided by our reactant here, equals 7.4 times 10 to the 8. Again, we have these numbers from our previous calculations. So that was 3.8 to the minus 6. The silver we're looking for, and our S2, whoops, wrong way. S2 was 2.86. 2.86, and that's going to equal 7.4 times 10 to the 8. Again, you basically the silver and the Kf switch places. That gives us that the silver would equal 3.8 times 10 to the minus 6 divided by 7.4 times 10 to the 8 when you rearrange it correctly, 2.86. And finally, we get down to this number here, which based on our assumption should be a small number. So let's see how we did here. We end up with 1.8 times 10 to the minus 15 molar would be our silver concentration. And it does make sense. Again, the silver should be pretty small there. I think I missed a number there. Hang on here. I think I wrote the wrong number in there. Hang on here. I did. I wrote this number 9. I'm sorry. This is 9. That's bad. That's 9. And that's a 9. There you go. Not a 6. That's a 9. And that makes that an 18. There you go. Thank you. So yeah, I had it on my calculator. I just wrote it wrong. So that this number here that we just calculated previously was 3.8 times 10 to the minus 9. And obviously that's the number we should carry over here to give us our 1.8 times 10 to the minus 18 molar. Question on that, and that is a very small value of silver, which makes our assumption be correct in that case, and that's what we would expect to occur. Any questions on that there? Okay. So we'll take a break right now, and we're pretty much have only one more example to go. So we will continue with this at the beginning of lab. We'll finish up talking about this example, and I'm going to show you the other way you could kind of approach to get the same answer here. And we'll do the last example, and then we'll be done with this chapter. And then after that, we will talk about part 2 of the buffer experiment. So for now, we'll stop and make sure you put here if you haven't done so, and I'll see everybody in about 20 minutes or so.